Here we are with section 6 of chapter 3, our last section of this chapter involving exponential and logarithmic models is the title of this section. We're going to look at a few more application problems, a few situations that involve exponential and logarithmic functions. We've already seen carbon dating. We have logistical gross, where the gross sort of hits an upper limit. The Richter scale. We'll also look at sound, measuring sound in terms of decibels, and then what else do we look at? The pH of a solution, whether it's considered to be an acid or a base. So we're going to get started with carbon dating, and as we mentioned before, the less carbon-14 that a substance contains indicates how long that organic material has been dead. Okay, so it says that the ratio of living matter is about 10 to the 12th power. Okay, and after once the organism dies, then carbon-14 starts to decrease, and so the ratio gets smaller. Alright, we're given a formula where R is the amount of carbon-14 left, and we can calculate the amount remaining based off of an exponential function, with t being the amount of time where the organism has been dead. So example 1 reads, estimate the age of a newly discovered fossil in which the ratio of carbon-14 to carbon-12 is R equals 1 over 10 to the 13th power. So we don't have to come up with this formula on our own. We're just given the formula. And so we write 1 over 10 to the 13 in the place of R, and that equals 1 over 10 to the 12th power times e to the negative t over 8,223. Okay, so what we want to do is just estimate the age. And that would be t. So we want to solve for t. If we multiply both sides by 10, or the entire equation by 10 to the 12th power, then what we're basically going to get, I'll just go ahead and write this out. We have 10 to the 12th over 10 to the 13th. Multiplying the right hand side by 10 to the 12th would just simply cancel out the 10 to the 12th for the right side, and we'd end up with only the exponential expression. If you recall the quotient rule, where we divide two exponential expressions having the same base, we can subtract the exponents. So we would take the 12 and subtract the 13 from the bottom, combining them into one exponential expression. And this is 10 to the negative 1, which can be written as a tenth. Okay, so the original amount of carbon-14 has been reduced by a tenth. Alright, so from here we have an exponential expression equal to 1/10. As in the previous chapter, the way we solve this is we convert it to a log function, logarithmic version of the same equation, and we write the log equals the exponent, negative t, divided by 8,223. The base of the exponent becomes the base of the log, so log base e. We could have written the natural log instead. And then the left-hand side of the previous equation becomes the argument of the log, 1/10. And so rewriting this one more time, we have the natural log of 1/10 equals negative t over 8,223. To solve for t, we would multiply both sides by 8,223. The 8,000 would cancel on the left, leaving only, or on the right, leaving only a minus t. And so then we'd have the 8,000 times the log function. And now we just multiply both sides by a negative. We swap the negative sign over to the left. And we have the exact solution for t. However, we want to get a better idea as to how many years this is. So with our calculator, we enter in the natural log of 1/10, and then we multiply that by negative 8,223, and we see that t equals 18,934 approximately. So approximately 18,000. Let me go back, I forgot the number already. 934. And this is in years. Alright, so we can apply what we've learned about exponential and logarithmic equations to solve problems involving carbon decay, carbon dating. Example 2 involves sound, and the decimal reading of a sound is 10 times the log of the intensity of the sound divided by I naught. Okay, and I naught is simply 10 to the negative 12, and it is considered to be the lowest intensity sound that we can hear with human ears. So in example 2, it says find the number of decimal from a conversation with an intensity of 2.1 times 10 to the negative 9 watts per meter squared. Watts is a measure of power, and meter squared is a measure of area. So when you make a sound, it spreads out over a particular area, and as that area increases spherically, you could say, in all directions, the power of the sound gets distributed over a larger and larger area, and so as the sound propagates farther from the source, it gets less audible. Okay. So let's see, what are the decibels? Decibels are represented by D. We multiply 10 times the common log of the intensity of the sound, which was given 2.1. I'll write e to the negative 9. E is in place of times 10 and the exponent negative 9. You could say that e stands for the exponent of the 10. And then I naught, which is 10 to the negative 12. Or if you wrote that in the same format using the e symbol, you could write 1 e to the negative 12. Okay, so all we do is put this expression into our calculator, which we do not have to use change of base. The decimals of a sound are based off of the common log. So we have 10 times the log of 2.1, and the double E button is located above the apostrophe, I think, or this could be the comma. But you have to hit second to get to it, and it only enters one E, but there's a double E symbol. So once you do that, you can enter the negative 9. It's just a quicker way to enter scientifically notated numbers. And now we divide that by the I naught, which is 1 e to the negative 12. Enter. So the decibels read 33. B reads, find the number of decibel from an explosion with an intensity of 5.3 times 10 to the negative 2 watts per meter squared. So we write D for decibel, and 10 times the log, 5.3 e negative 2, shorthand way of writing it into the calculator. And then we write I naught, the intensity of the least audible sound, in the denominator. And from here we simply use our calculator. Write 10 times the log of 5.3 double E button negative 2. So you would expect the decimals to be really high versus the conversation that we calculated in the previous example. We should get a higher decibel reading. So 1 times e to the negative 12, enter. And we do. We get 107 decibels. And this should be dB per decibel. Okay, so that was just a matter of evaluating a function at a particular input, and we simply input the intensity. So even though the intensity of an explosion in this case was almost 10 million times larger than the conversation, the decimals of the conversation are only a third of the decimals for the explosion. So the decibels simply just take the intensity and they put it on a different scale, a log scale. Exercise 1 reads, a shouting sound is 5 decibels louder than a normal conversation. How many times larger is the intensity of the shout than that of the normal conversation? Well, up above, for a normal conversation, we calculated 33 decibels. Okay. And then for the intensity, we were told 2.1 e to the negative 9. So what kind of intensity would we get for a shout? That's what we want to solve for. And we're told that it's 5 more decibels, so D would equal the normal conversation plus 5, which gives us a decibel reading of 38. And now if we use that in our formula for the intensity of sound, we get I over I naught. Okay, log of I over I naught times 10. And we want to solve this for I. I naught is understood to be 10 to the negative 12. We could write that if we wanted to. And so our first step is to get the log expression by itself on one side. So we have to divide by 10 on both sides. Divide by 10, divide by 10. This gives us 3.8 equals log of the intensity of the shout, and this is what we're looking for. Okay, I use the I with the subscript S for shout, and that gets divided by 10 to the negative 12. And now if we convert this to the exponential form of the equation, we would write 10, which is the base of the common log. Log equals the exponent, so 3.8 would become the exponent of the 10, and that would be equal to the intensity of the shout divided by 10 to the negative 12. And now to solve for this intensity, we multiply both sides by 10 to the negative 12. So I've ran out of room over here. I'll simply write the intensity of the shout equals 10 to the power of 3.8 times 10 to the negative 12. Okay, what do we get? We'll pull up our calculator and write 10 to the 3.8 times I want to get out of the exponent, so arrow right, times 10 to the negative 12th power, and we get 6.309. I'll round it to 6.31. E means times 10 to the negative 9. So this intensity of the shout is 6.31 times 10 to the negative 9. Well, the question is, how many times larger is the intensity of the shout than that of the normal conversation? We know the values of each individually, but how many times more is one than the other? So what we do is we write a ratio, I shout divided by I, and we could put NC for normal conversation. We make a ratio of them if we want to know how many times larger one is than the other. And we divide the values that we got. The normal conversation intensity goes on the bottom, with a 10 to the negative 9 on the top and bottom. You could say that those cancel out, and we just calculate 6.31 divided by 2.1. Bringing our calculator back, 6.31 divided by 2.1 equals about 3. Okay, so if we rearrange this, what we have here is I shout divided by I of normal conversation equals 3. If we move the 3 over and we say we want to solve for the intensity of the shout, then to do that we would just take both sides and multiply by intensity of normal conversation. The intensity of normal conversation would cancel on the left, and we could read exactly what the question asked us. Intensity of the shout is 3 times the intensity of the normal conversation. So when you're asked about how many times more is one thing than another, you simply just make a ratio out of the two values. Now we move on to pH scale, and we're given the formula. The pH of an acid or a base is the negative common log of the concentration of H plus ions. So the pH of water is 7. Acidic solutions have a pH less than 7, and basic solutions have a pH greater than 7. Example 3 says compute the pH of a solution with a hydrogen ion concentration of 2.63 times 10 to the negative 7 moles per liter. Is the solution acidic or basic? Okay, pH equals a capital H minus the common log of the concentration, 2.63 E negative 7. So minus, if you start out with a minus for the expression, you don't want to use the subtract symbol. You want to use this key here that's grouped with the number keys. Common log 2.63 times 10 to the negative 7, enter. We get a pH of 6.58 approximately. So I'll change this equal sign to approximately 6.58. So with a pH less than 7, this would be an acid. What is the hydrogen concentration of a solution with a pH of 10.3? So here we actually replace the pH on the left side of the formula. We write 10.3 equals minus log of H plus. So we have to convert this to an exponential. And first we're going to move the minus over to the left, group it with the 10. So now we write negative 10.3 equals log. We want the log to be completely separate. No other numbers on the side of the log expression, just the log expression with its base and its argument. And now we convert this to an exponential equation. You note that this is the common log, and it's understood to have a base of 10. And so on one side of the equation we write 10 as the base of our exponent with an exponent of negative 10.3, and then the result of that would give us the H plus, the hydrogen concentration. So from here we simply use our calculator and we enter 10 to the negative 10.3, and we get approximately 5.01 times 10 to the negative 11. H plus equals 5.01 10 to the negative 11. So with a pH of 10.3, much higher than 7, this is a base. Okay, and so it has a very low concentration of hydrogen ions. Exercise 2, how many times is a solution of pH 2.5 more acidic than a solution of pH 5.1? Well, let's calculate the solutions. The H ion concentration. So we write 2.5 equals negative log of the H plus concentration for, let's see, this is for the 2.5, and then again for the 5.1. These are both acidic, but one is more acidic. The 2.5 solution is more acidic than the 5.1. So what is the difference? How many more times is one's concentration than the other? Well, as we did in the previous problem, we moved the minus sign over to the pH reading. So for this one, we get a negative 2.5 equals log of H plus. And then we have a minus 5.1 equals log of H plus. I just didn't write the brackets. H plus is one variable. Okay, the H plus is really just a label. So we convert both to an exponential. Common log has a base of 10, so this would be the base of our exponent. And so we write negative 5.1 equals H plus. And same procedure with this one, the 2.5 pH solution. We have 10 to the negative 2.5 equals H plus. So the question was, how many more times is one than the other? So I'm going to write H 2.5 subscript divided by H 5.1 equals, and we have 10 to the negative 2.5 divided by 10 to the negative 5.1. What does that give us? 10 to the power of negative 2.5, enter, and then we divide that result by 10 to the negative 5.1, enter again, and we get 398. So if we rearrange this, we can show that the concentration of the more acidic solution is about 400 times the concentration of the 5.1 pH solution. Okay. Our last few examples here on our last page of 3.6, we look at logistic growth. And if you plot one of these logistic growth equations with your calculator, you'll see that it doesn't increase. Well, it does increase indefinitely, but not at the rate of a normal exponential equation. It sort of flattens out and reaches a limit as t approaches infinity. It sort of looks like this. If this was your y-axis and here was your x-axis, it's going to do something like this. It's going to go up and then it's gradually going to flatten out like that. Okay, this is logistic growth. So example 4 uses this type of formula to describe a group of birds and its population. It says that the population of the birds will grow according to this formula, which matches the formula we were given above, where C equals 210. A, just some multiple of our exponential expression on the bottom. We have A equals 6. And then we have a rate K, and in this case it's 0.12. Okay, T is given in the number of years. So what's the population of the group in the beginning? Okay, well, in the beginning 0 years have passed, so we simply calculate A of 0, and so we get 210. 1 plus 6 times the natural exponential expression. Then we have the rate 0.12, but t is 0. And so 0 times 0.12, negative or not, we're going to get an e to the 0. And anything raised to the 0 power is just 1. So e to the 0 gets replaced with 1. And we end up with 210, and 6 times 1 plus 1 is 7. And we end up with a population of 30. So you can't just look at the formula that we were given and pick out the beginning population. Okay, you actually have to enter t equals 0 for the years. And so it's pretty easy to calculate. With t equals 0, the e to the 0 reduces to a 1. So definitely not that bad of a calculation. You can do it without a calculator. Alright, what would the population be in 10 years? So we're calculating A of 10. And here we simply enter in a different number for t. So we have 210 on the top. We have 1 plus 6, and 10 times 0.12 would be a negative 1.2. And I can't do that in my head. So we'll use our calculator. And we'll type in 210 divided by, you may want to put the denominator in parentheses, 1 plus 6 natural exponential expression with a negative 1.2 as the exponent, arrow over and close your parentheses, and now we just simply hit enter, and we get, if we round it to the nearest whole number, we get 75. So in 10 years our population increases from 30 to 75 birds. C, graphical only, we'll actually plot our function in the y-editor and look at the graph. And we want to know what the population will be, or no, we want to know when. Okay, we want to know t, the number of years it takes to reach a population of 180. So there's not really anything to write here. Okay, we just pull up our calculator and we go to our y-editor. We type in our logistic function, 210 divided by, and again you may want to put the parentheses on the bottom around the numerator, 1 plus 6 times e to the negative 0.12x. So keep in mind, we'll save ourselves a lot of trouble without swapping variables. We'll just use an x in the place of t. So keep that in mind when you interpret the graph of this function. We now hit graph. And as always, we don't see anything, okay? But we do have some values to go by. We know that in 10 years our population is 180. And our population is red on the y-axis, and so we can put in a little bit bigger number for y max. Let's say 250. Okay, a number bigger than 180. And then how many years did it take for, well, let's see. How many years did it take in the previous problem? 10. We're not going to put in negative years. Let's put in 100 years. Well, actually, let's put in 100, a number bigger than 180. Let's put in 200. Okay, because x represents our time, and we want, well, no, the 180 is our population. Okay, so y is our population. We entered a number bigger than 250. Your guess is as good as mine as to how long that's going to take. So let's go with 200 and see what we get. And as you can see, I didn't lie to you, logistic functions sort of reach a maximum level, and then they still increase beyond that point, but not by much. So let's trace along this curve, and let's scroll back to where we find y equals 180. Y in our calculator represents A from our workbook, and so there we are. 179.76 is close enough to 180. We get approximately 29.78 years. X is our time t, so graphically we say that t equals, let's round it to 30 years. We could trace and type in 30 exactly, and it's really not much closer to 180 than 29 point something something was. We'll just go with the whole number, 30 years. So in 30 years, A, or the population, equals approximately 180. And then we could say approximately 30 years if you wanted to be picky. Okay, D, what would happen to the population in the long run? So if we trace along the function, as we go to the right, we increase our time. So in the long run, as time increases, x becomes bigger and bigger. You can see that we hit a limit for the population at this point. 148 years into the future, we have a population of 209.99999. which if you round it, you get 210. And at this point, we went so far that the calculator just goes ahead and gives us the value of 210. Okay, it probably rounds it. So in terms of a logarithmic formula, you can see that we have c in the numerator of our fraction, sort of the upper limit of our population. Okay, 210. And then on the bottom, the rate and the 6 probably has something to do with how fast we approach that limit. So here we would say A equals 210 in the long run. And that completes section 6, and it completes chapter 3 for exponential and logarithmic functions.